Okay, let's keep going. A couple different kinds of launches. You can have, for example, horizontal launches that might be like off a cliff, where your object goes goes like this, crashes to the bottom. Maybe it's got a height h, maybe it travels a distance x, but you know that vertically and horizontally it's got different kinds of motion. It's going to have a velocity off the edge too. But vertically, doesn't matter what the velocity off the edge is, vertically it's going to have a velocity of 0 meters per second as its initial velocity, but that is going to change as its acceleration is negative 9.8 meters per second squared. So every second its velocity decreases by 9.8. It travels a distance equal to negative h by the time it hits the ground, but you could look at it at different times. Maybe it doesn't travel that whole distance. That's totally fine. These are definitely going to be true. Horizontally, its velocity is going to be constant. So VI is going to equal V final, and that's just your velocity off the cliff's edge, and it travels distance equal to x. Now you're probably not going to know all these variables, nor do you need to. If you know the height, you can figure out the time. You can just say, hey, d equals VIT plus 1/2 AT squared, but the VI is 0, so you get d equals 1/2 AT squared. If you know x, though, you can still get like the velocity if you know the time or something like that. So there's different ways to do it. Figure out what you know. Like always look at these, and you typically need 3 variables. What do you know? If you know horizontal velocity and distance, you get the time, you take the time, put it into vertical motion. Or if you know the height, you can figure it out. It will follow that distance h in the same time, so time doesn't depend on a lot of things. Doesn't depend on velocity off the cliff, right? If it was an angled launch, it would, but here it doesn't, because that velocity is all horizontal. It doesn't depend on mass. All objects fall at the same rate. It doesn't depend on the object's color or odor or anything else like that. The time it takes to reach the ground depends only on the height, if you know your acceleration is negative 9.8 meters per second squared. You could deal with angled launches as well. An angled launch would be like this. Boom, goes up, we know our velocity, we know our angle. Let's say our velocity is 40 meters per second. Let's say our angle is 30 degrees above the horizon. And so it follows in a parabolic path like that. Boom, hits here. That would be your max height. Your initial velocity, you can break into components. You got a v sub x and a v sub y. V sub x is v cosine theta. V sub x is v sine theta. Sorry, v sub y is v sine theta. So if we do that, v sub x is going to be your horizontal motion, and that would be 40 cosine 30 degrees. I'm putting the degree symbol in. Vertical motion is going to be v sub y, which is 40 meters per second. I need to put those units in too. Sine of 30 degrees, so that equals 20 meters a second, and this equals 34.6 meters per second. How long does it take to reach the max, for example? Max height. Well, let's think about this. For max height, we're going to want to work vertically, because we know vertically at the top, v sub y is equal to 0. So you can say, okay, well, it starts at 20, and to get to 0, it's about 2 seconds. We could be like, okay, well, let's be precise. Vf equals Vi plus At. So 0 equals 20 meters per second plus negative 9.8 divided by, times time. So time is going to end up being negative 20 over negative 9.8. So you're probably going to go about 2.1 seconds to hit the ground, to reach the height. And you can figure out what it is pretty easily. There's different ways to work the kinematics here. So if it takes 2.1 seconds to reach the top, that means it's going to hit at twice that. So it's going to hit at 4.2 seconds. So when it hits, a couple things you know. Time is twice the time to the max height. You also know V final in the y direction is equal to negative V initial in the y direction, meaning if you're looking at the vertical motion here, vertically, V final is going to be negative 20 meters per second. 2.1 seconds up, 2.1 seconds down, its velocity is negative 20. You also know that the y displacement, I sometimes call it distance, but it's really a displacement, is going to be 0 meters. Because at this point, elevation is 0 when it hits. And so this really represents your displacement, your change in position. Your change in position is 0 if you're landing at the same height as which you started, or the same elevation. So if you start on a flat surface, you're going to end on the same flat surface. We can complicate things a little bit, but let's just keep it simple enough for now. Another kind of motion that we sometimes see is circular motion. This is pretty straightforward. The difference being, for circular motion, even if speed is constant, and it's usually going to be constant, velocity direction changes. And if its direction changes, that means you have a net force and you have an acceleration, and they are both towards the center of the circle. Earth pulls the moon towards the center. The sun pulls the earth towards the center of the circle. So let's say your object is here. That means your acceleration and your net force are both inwards. If your object is here, your net force and your acceleration are inwards. Your velocity, though, is tangent to the circle. Meaning, at this point, let's see, whoosh, that would be your velocity. At this point, that would be your velocity. They should be the same length. They're not, I'm sorry. That means if that force suddenly disappeared, your object would just keep going. Object in motion stays in motion the same direction, so it would just keep going like this. Or this one would just keep going like that. Now, we know with this, centripetal force is really just your net force. And net force is just mass times acceleration. And these are basically just concoctions. There really isn't a force called the centripetal force, or even a force called the net force. They are caused by other forces. And those other forces could be, for example, gravity, if you're talking orbits, or it could be tension, if you're swinging something around on a string, etc., etc. But because it's equal to an equivalent to the net force, we can do F sub c equals ma, or F net equals ma, which leads you to, I mean, this equation right here, there's an F sub c equals ma sub c, so there's sometimes what we call the centripetal acceleration. And centripetal acceleration, the cool thing about this is we have a way to explain it, which is just v squared over r. So that is equal to your velocity squared over r, which means that F sub c, which is equal to ma, should be mv squared over r. This is not on the reference table here, but this one is. The one other thing you occasionally need to know is that velocity might be the distance around the circle divided by the time to circumvent the circle, and so the distance is just going to be the circumference, 2 pi r, divided by time, which is the period t of one rotation. So sometimes this comes up. Now, we talked a little bit about gravitational forces already. Let's extend this, because often, like, gravitational force is what keeps objects in circular motion. We said before it's equal to mg, right? Where g can be a different value on different planets' surfaces, but tends to be constant. But there's a more general equation for gravity. And this is F sub g equals big G, m1, m2 over r squared. So you always have two objects. They pull on each other with equal force. This is an application of Newton's third law. Every force has an equal and opposite force, but not necessarily equal accelerations. The Earth has a much bigger acceleration than the Sun does as they orbit. The Sun gets pulled on the Earth, and the Earth gets pulled by the Sun, but the Sun's so massive that it doesn't have a whole lot of acceleration, because we know acceleration is equal to net force over mass. And for most objects in orbit, there's only one force. That would be F sub g. So your net force is going to be F sub g, which is A F net over m. So equal force but not equal mass. If you found F sub g, you could say A, the net force, the acceleration of Earth is equal to the gravitational force on Earth divided by the mass of the Earth, for example. That totally works. So in fact, it just ends up being your acceleration is g times the center mass over r squared. G is equal to universal gravitational constant 6.67 times 10 to the negative 11th newtons times meter squared per kilogram squared. You're not going to use this much unless you need to do these calculations. This is, though, for example, what we call an inverse square law. And so we see things like F sub g is proportional to 1 over r squared, which is to say inversely proportional to r squared. If we left, g is constant, right? But if we left m1 and m2 constant and we changed only r, we would see a relationship like this, F versus r, looking like that. If you instead changed just one of the masses, which usually isn't possible, but you can make believe, F versus m, well, that's a direct relationship. F is directly proportional to m. We'll just ignore everything that's not m. So you get a direct relationship or a linear relationship. So let's take this. Let's say you want to find F sub g. Don't forget that E button on your calculator. G m1 m2 over r squared. Oftentimes numbers you need are on the reference table if you can't figure out what they are. So let's say it's Earth Moon system, right? 6.67 times 10 to the negative 11th. You'll see protons and electrons masses on here too, neutrons also. What is the distance Earth to the Moon is there. So that's your R, 3.84 times 10 to the 8th meters. That's squared. Don't forget that square. Newtons times meters squared over kilograms squared. Don't get confused. Don't use the radius of the Earth. R says you might think it's a radius, but it's just the distance between the center of two objects. If you are on the Earth's surface and you want to find the distance between you and the Earth's surface, that would be distance radius of the Earth. But this is the distance Earth to Moon. And then we see the Earth's mass right here, 5.98 times 10 to the 24th kilograms. And the mass of the Moon, 7.35 times 10 to the 22nd kilograms. You do all the math, you get a big number. I don't know what it is off the top of my head. But what you do end up finding out is that because this is such a big number, such a small number, negative 11, you're constant, you need really big masses in order to have big forces. So that's why, generally speaking, you throw like, PB and J, like peanut butter and jelly jars, near each other. They might both have attractive forces towards each other, but that's very, very small. So you're probably not going to notice it. You can also look at changes in force as you change variables. So F sub g equals g m1 m2 over r squared. So what if you double r? Well, there's different ways to go about this, but just imagine for consistency's sake, you ignore G, and because F is proportional to M1, M2 over R squared. And so originally you might have, like, let's just pretend our mass is 1 times mass 1 over radius 1 squared is 1. Now we double R, let's see how it changes. We got 1 times 1 over 2 squared, so it's 1/4. So doubling R gives you 1/4 the original force of gravity. So it's a lot less. Tripling it would give you 1/9 if we change this to a 3 squared. 1 times 1 over 3 squared equals 1/9. You can start doing multiple changes. So if you like double R, you know what, let's have R and have M1. So now you have, originally you started with 1, 1, 1. Now we halved M1, so that's 1/2 times 1 over, we halved R, that's 1/2 squared. So you end up getting 1/2 over 1/4. State change flip, that gives you 2. So you basically doubled the force. So even though one mass is smaller, because you're closer by a factor of 2, you actually have twice as much gravitational force. We've talked about forces a bunch already. Let's hit a few others that we haven't gone over too much. The normal force. So think about balance versus unbalance. Let's say that there's a weight of 100 newtons and it's balanced. And even if it's balanced, even if it's unbalanced horizontally, it's probably balanced vertically, meaning even if it's accelerating to the right or left, it's probably not coming off the table, which tells you your normal force has got to also be 100 newtons. So you can have balance in one dimension but not the other. Sometimes you won't have balance. So let's say you have an elevator. And you still have 100 newtons down. Well, maybe that elevator is accelerating upwards with acceleration of 2 meters per second squared. Well, let's figure out the mass of this object first. So m is equal to F sub g over g, which is going to be 100 newtons, because if it's a 100 newton object, that's weight is 100 newtons, over 9.8. So that's about 10 kilograms. I'm going to just round it to 10 to make it easy. So that tells you you're accelerating up at 2 meters a second, and therefore your net force is ma, which is 10 kilograms times 2 meters per second squared, or 20 newtons up. So if your net force is 20 newtons up, what's your normal force? Well, this is the picture. You got 100 newtons down, you got some amount up, and you know that they add up to be 20 up. So something up minus 100 down equals 20 up. Well, that something up has to equal 120 newtons. It has to be 20 bigger than what's down. So you got 120 newtons. What if instead your acceleration is 2 meters per second squared down, right? Well, you're still going to have a net force of 10 kilograms times 2 meters a second, but it's now going to be 20 newtons down. And your object still weighs the same amount. Its acceleration doesn't affect its weight in any way. So you get 100 newtons down, but you know that you have to have 20 down larger than you have up. So that tells you you have to have 80 newtons up. So your normal force is changing to match your acceleration. So 80 newtons up, 100 newtons down. Now sometimes you can go on inclined surfaces. And so for an inclined surface, let's say you still have a 100 Newton box. Note, it might not even tell you that its weight is 100 newtons, and just saying 100 Newton box, you've got to recognize that that adjective 100 newtons is the object's weight. And even though it's an incline, its weight still points straight down. But the angle, the 90-degree angle between the surface is changed, so now your normal force looks like this. And we can even give this an angle theta here, and that angle theta is the same as that angle theta. So that's your free body diagram if there's no forces. And again, your mass is your weight over g, 100 newtons over 9.8, which is about 10 kilograms. We're going to round. So 10 kilogram box, right? Now, if we break this into components, like this is your free body diagram right there, FBD. If I break this into components, well, let's say we have a component of weight S sub g parallel to the surface that pulls it down the incline. And we have a component S sub g parallel that pushes into the surface. Well, that's still 100 newtons, right? Let's say now theta is 30 degrees. Well, this right here, that angle 30, so this should be 100 newtons times the sine of 30. And this is not on the reference table, so you need to know this, which is going to be 50 newtons. This component into the surface is going to be F sub g cosine theta. So 100 newtons times the cosine of 30 degrees, which is going to be 86.6 newtons. Well, let's think about this. This is balanced and unbalanced in some directions, and it's easiest to think about this if you redefine your y-axis as going along the same direction as the normal line, and you redefine your x-axis as going down the incline. And in the y direction, it's going to be balanced, meaning it's not accelerating off the surface. If at anything, it's going to slide down the surface, but it's not going to slide off the surface. So if it's balanced, that means that your normal force has got to be equal and opposite to your component of the weight perpendicular, so that's equal and opposite to 86.6 newtons. So your normal force has gone down as compared to the flat surface. On the flat surface, your normal force was equal to the weight. They were both 100 newtons. Now you still weigh 100 newtons here, but your normal force has gone down because some of that force is being used to pull it down, and that would be your force down the incline of 50 newtons, meaning your net force, which is the remaining of all your forces, you add these forces together, well, that cancels this component. The only thing that's left is F sub g parallel is 50 newtons. And then you could say, hey, what's my acceleration? Well, my net force times my mass, so that means my net force is 50 newtons, my mass is 10 kilograms. Wait, sorry. Made a mistake there. Take this here. A equals F net over m. That wouldn't have made sense. Can't have an acceleration over 9.8 meters per second squared. Okay, so my net force is 50 newtons. My mass is 10 kilograms. Divide that, we get 5 meters per second squared. So my acceleration down the slope would be 5 meters per second squared. But what if it's not moving? Well, there's going to be a reason, right? So let's call it friction. Due to friction. What if it's not moving? Well, my free body diagram looks a little different now. We still have a normal force. We still have a weight. Now we get a frictional force. So let's think about it. If it's not moving due to friction, you still have components down here. Well, that tells you your frictional force, because it's now balanced in the x direction as well. So your frictional force has got to be F sub g parallel, which is 86.6 newtons. What did I do wrong? Okay. Sorry. F sub g parallel is 50 newtons. That didn't feel right. Okay. So that means your force of friction is 50 newtons. What if it's sliding at a constant speed? Again, it's still balanced. So your free body diagram looks exactly the same, and your force of friction is still 50 newtons. So you might ask yourself, what's the difference? Well, if it's not moving, that means this is static friction. And if it's moving at a constant speed, it's moving, so now you have kinetic friction. Two different kinds of friction. You want to even get more complicated? Take the same question. 30 degrees, 10 kilograms, 100 newtons. That's 86.6 newtons. There's the force of friction. What if A, your acceleration is 2 meters per second squared down the incline? Well, let's see what the net force is. Net force is MA. So 10 kilograms times 2 meters per second squared is going to give me 20 newtons. So what is the frictional force? Well, let's think about it. That component of weight is going to be 50 newtons. That is going to be balanced out, and this is what I'm going to call the x direction right here. So x direction, you have down the incline, you got 50 newtons. Up the incline, you have a force of friction. And the net force in that x direction is going to be 20 newtons. So you say, what's 50 minus my force of friction has got to equal 20 newtons. So your force of friction has got to be 30 newtons. 50 newtons down minus 30 newtons up gives me a net force of 20 newtons, which is what I found through F equals ma. If you want to take this a step further, you can start introducing laws of friction. So we saw the fun equation, F sub F equals mu times F sub n, where this is a coefficient that depends only on the two surfaces. So mu is going to equal F sub F over F sub n, which in the last situation was 30 newtons over 86.6 newtons. So that is our force of friction. So we divide 30 divided by 86.6, which gets us about a third, 0.35 would be our coefficient. No units on that, right? Now sometimes you find that coefficient from the first page of the reference table. Like you see different materials here. You can see rubber on concrete. You can see rubber on wet concrete and dry concrete. Kinetic versus static. They have some blanks for static. I don't know why. Let's keep it simple though, because we know kinetic is moving. We know static is not moving. So this is all in friction. So let's say you have a box. Maybe you have 100 newtons down. Maybe you have 100 newtons as your normal force. So what is your force of friction kinetic? And we'll say it's wood on wood. Well, look at this. Kinetic, wood on wood, 0.3 times your normal force, which is 0.3 times 100 newtons, or 30 newtons. So, depending on which way it's going, if it's moving to the right, could be sliding to the right, the force of friction will be to the left, 30 newtons. Could be sliding left, its force of friction would be the right, 30 newtons. You could be pushing it, but it doesn't have to be. It could just be sliding. Remember, its velocity doesn't have to be in the same direction as its net force. And your kinetic friction is pretty much always going to be the same, and you can use that equation if you know the two variables. You can use that equation to figure things out. But sometimes it gets a little more complicated. So let's take this box here. 100 newtons, 100 newtons. And let's say you're applying a force to the right, and you want to find what the static friction force is. Well, we know the coefficient is 0.42 for wood, right? So static, and there's a word max I'm going to add here. 0.42 times 100 is 42 newtons, right? But that doesn't mean that's your actual force. That is not your actual force of static friction. Because you need balance, right? You need balance in your universe. So if your applied force is equal to 10 newtons, you cannot have 10 newtons to the right and 42 to the left. That would imply friction was moving it in the opposite direction, which makes no sense. So that tells you that this is the max. If you apply 10 newtons, your force of friction is 10 newtons. If you apply 20 newtons, your force of friction is 20 newtons. What happens if you apply 42 newtons, right? If you apply 42 newtons, well, that is the point at which it starts moving. Maybe you need just a tiny bit over 42. Then it starts moving, and suddenly you are back to the situation where we had on the last page, where as soon as it starts moving, you've got 30 newtons of force. But you could apply 40 newtons, and your force of friction would be 40 newtons. But if you apply more than 42, it starts moving, and then you're dealing with kinetic friction. You could have situations, again, where it's balanced. So sometimes there's different ways to find it, like, hey, constant speed. Important word, we see that. Let's say you apply 20 newtons. You got 100 newtons, 100 newtons. You could even say that it's a wood block, but they probably won't say it's on a wood table. And that tells you if it's balanced, then your frictional force has got to be 20 newtons backwards, because your net force is going to be 0. It's going to be balanced. And so understand that words like constant speed are very important to recognize. They tell you important things about the situation that you're dealing with. Okay, let's move on to momentum. And so momentum is defined as, I think I'm missing a page here in my notes, but momentum is defined as mass times velocity. Impulse goes by letter J. So momentum goes by letter P. It's mass times velocity. Impulse goes by J. It is the change in momentum, which is